afternoon, everyone. So now I am going to discuss about open circuited PN junction diode. So here, the open circuit PN junction is, as I told you previous class. Same thing here also. We have to discuss about P-type material and N-type material. They are combined to each other. Then it is formed as a PN junction diode. The basic phenomenon for this formation of P-type and N-type device. Let us see here. First point, let us go through the first point. In a piece of silicon crystal, if one half is doped by P-type impurity and the other half is doped by N-type impurities, a PN junction is formed, right? Okay. So here, in P side, the doping concentration impurities are nothing but trivalent impurities. Basically, it has acceptor property. Coming to the N side, so here the doping concentration nothing but those materials are doping into this particular N-type device such as pentavalent impurities doped in this particular other half side of this particular device. So this is the complete structure is taken a piece of silicon crystal. By doping half part with the trivalent impurities atom, then the P-type device, P-type side is formed, and next one the other half is by doping the trivalent impurity atom, then N-type device is formed. So those two are combined to each other, then it is nothing but PN junction diode. So here, let us observe in P side, the concentration of holes is more. So these are the hole. This is nothing but electron. So let us observe here, the holes are majority charge particles here. More number of charge particles compared to the electron in P side. So the majority charge particles are here, holes, and minority charge particles are electrons. Okay. Here, the concentration gradient of holes is more compared to electron here. Coming to N side, so here, these are the electrons. This is nothing but hole. Let us observe here, the majority number of charge particles in N side are electrons and minority charge particle nothing but hole. Okay. So let us observe the second point here. Here, the concentration of hole in the P side, nothing but it is anode terminal, is much greater than that of N side. Similarly, the second point is the concentration of free electrons in the N side is much greater than that of P side. Okay. So here the N side we call it as cathode terminal. In P side, we are call it as anode. So means the cathode is negative. Okay, the cathode is negative and the anode is positive here. Here the cathode, it is the negative terminal. This is the basic formation of the particular PN junction. Next, so here the electron diffusion from N side to P side. As I told in previous class also, the electrons are diffusion because of the concentration gradient. Due to the concentration gradient of majority charge particles are here, nothing but electrons. Here the majority charge particles are holes. They are diffused towards the lower concentration gradient. Here majority are holes in P side. Here the minority are holes in N side. So compared to these two, P side Fourier concentration is more compared to N type. So means these holes are moving towards this N side. Okay, like similarly here the electrons are more compared to P side. So the Fourier concentration gradient is more here and the Fourier concentration of electron is low here. Then the majority charge particle electron move towards the P side. Okay. Then what happens? When the holes are moving from P side to N side, then the positive immobile ions are formed near to the junction. That will be shown in next slide. And similarly, the electrons are moving from N side to P side, then the negatively charged particles are formed near to the junction. Okay, so this is the first discussion about the particular PN junction diode. Similarly, last point, why the holes diffusion from P side to N side recombine with the donor atoms. Why? Because these are the trivalent impurity atoms, means one vacant position is there. That vacant position is added by the another charge particle. Here, the pentavalent means they are forming two bonds. One more is nothing but it is a free, that is donate to the other. So means it having the donor property, having the acceptor property. So let us see here. So when those are what I seen in previous slide, the majority charge particles are holes. They are moving from this side, that is N side. The majority charge particles are electrons. They are moving towards the P junction. What I told you in previous slide, the negatively immobile ions are formed near the junction. These are the negatively immobile ions. When the holes are moving from P side to N side. Why they are moving from P side to N side? Due to the concentration gradient. Okay, concentration gradient means here the larger number of holes are more, here very less amount of holes are available. So there is a lot of space, there is no space generally. So then the holes are moving from P side to N side. Then they form here immobile ions as positive charge particles. Okay. Similarly, here the concentration gradient is more due to the major charge particle such as electron. Here, compared to this side, P side, here the minority charge particles are less. So here the less carrier concentration due to the electron. Then the electrons are moving towards this side. Then they are forming here positive charge ions. When the holes are moving towards the direction, the negative ions are forming near the junction. So this junction is nothing but depletion region or barrier potential region or cut-in region. Okay. Let us see here. Let us observe the polarities. Here is nothing but negative polarity. It is nothing but positive polarities. So in this region, there is a electric field is generated. This electric field develop the potential difference across this junction. When the electric field is generated, developed here, the remaining further majority charge particle from N side and further majority charge particle further majority charge particles are holes doesn't pass away this junction. So this junction is act as like a wall. Okay. But after this, as I told you previous class, the P side is nothing but anode. It is positive. Coming to the N side, this is repelled with the negative terminal. It is cathode. Negative charge terminal or cathode terminal. Positive terminal or anode terminal. Okay. This is the PN junction diode, open circuited PN junction diode. Let us come here. At the thermal equilibrium condition in the region near the junction, further there is a no charge carriers moves. This region is called depletion region, barrier potential, built-in region or cut-in voltage. Okay. Next, second point. Due to immobile ions at the P junction, near the junction, P side and N side, there exists an electric field across the junction. So the barrier voltage, nothing but this potential difference is for silicon 0.6 volts, for germanium 0.3 volts, for GNR 0.25 volts. Like previously what I said, what I told in previous class, there is a energy band diagram. In that energy band diagram, there is a forbidden energy graph. Whatever we are applying external energy, that external energy over to that electron volt, then only the charged particles are jump from valence band to conduction band, such as electrons. Like here also, whatever the voltage we are applying for this device, external voltage applied for this device, that voltage cross over this cutoff voltage or cut-in voltage, then only the device then only the device is changing its conducting properties. Okay, so this is the internal diagram for this particular concept. So by moving the charge particles from P side to N side, and N side to P side, the electric field is generated. the electric field is directed towards from P side positive immobile ions to negative immobile ions, and here is nothing but barrier potential. Okay, so this is the symbol of this particular diode. This is the symbol. At consumer point of view, is available in market. This is the symbol here. Okay, and here one more thing you can observe. Which one is cathode? Which one is anode? There is some confusion towards the students. So let's observe here. So this is the mark here. This mark is aluminum mark here or your mark. So this is nothing but this mark is represented as nothing but negative. Where this side is this mark is available, that area or that side is nothing but cathode. Remaining side is anode. So where the mark is available, that side you have to identify that terminal it as negative terminal that it says cathode. Okay, next. Next. Here, by applying external DC voltage, by applying the external DC voltage to electronic devices is called biasing. So let us observe the biasing condition of this particular PN junction diode. In previous slide, there is a open circuited PN junction. But open circuited PN junction is nothing but here. This is the open circuited PN junction. Here, the electric field is generated. Due to that electric field develop, due to the electric field, the minority charge carriers are from N side to P side, and the minority charge carrier here P side to N side. They are moving. This current is nothing but drift current. And the concentration gradient, there is also some current is generated. That current is nothing but diffusion current. At equilibrium conditions are without applying any external forces, particular PN junction there, then only we can say it has the open circuited PN junction there. If you are applying any forces or any voltage that is due to or by using batteries, positive terminal connected to the positive terminal, negative terminal connected to negative terminal, then only the device is changing, it's completely changing direction, changing its properties. It means nothing but biasing conditions. So let us observe the biasing here. Apply the external DC voltage to the electronic devices is called biasing. Here we can apply the external voltage by using battery. This battery is having two terminals, positive terminal and negative terminal. The positive terminal is given to the P side. So here majority charged particles are holes such as positively charged ions. So for positively charged area we can make the connection as positive terminal. Similarly, in N-type, the major charged particles are electrons, such as having negative charge. For negatively charged area, we can apply the negative terminal. Okay, so here based on that, applying external DC voltage, the PN junction is acting as two biasing condition. One is forward bias condition, and the one is reverse bias condition. For forward bias condition, this is the battery. For positive terminal is applied to the positive side area, negative terminal applied to the negative side area, then what happens? Okay, by applying this potential here, whatever the charged particles here available, such as negatively charged particle, for negatively charged area, we are giving negative terminal, then the majority charged particles are repulsing to each other. There is no way to move the divisor, there is no way to move the charged particles towards the where the devices are moving, the charged particles are moving. For negatively charged area, we are applying negative terminal, then the majority charged particles are electron here, they are repulsing to each other. There is the way the charged particles are moving towards the junction, Okay, similarly, at P side, we are applying positive charge particle, positive terminal. These are the majority charge particles are positive charge particles. They are moving towards the junction. So then what happens at the junction? The junction width is decreases. They are the majority charge particle from N side. They are hitting towards the junction. The majority charge particle here hold. They are hitting to the junction. then the resultant, the depletion region will be decreases. So let us see here in this diagram. By applying this voltage, the electrons are moving this side, the electrons are moving this side, and the holes are moving this side. Then the depletion region will be decreases. Okay, and the resistance of this potential difference is decreases. Okay, right. Let us observe here. The charge particles are moving in this direction. The charge particles are the electrons are moving. The electrons are moving in this direction. What happened? What we are expecting from this particular condition? There is a current. There is a current moving opposite direction of the electrons. This is the current. Opposite direction of the electron. Also, the whole current is also available, but practically we are considering only electron current. We are considering only electron current. Okay, so this is the forward current in a diode. So coming to the graphical one, VA characteristics, volt ampere characteristics. So on x-axis we are taking voltage, on y-axis we are taking current in milliamperes. Here it is voltage. This is for forward characteristics of silicon diode. Okay, what have we discussed here? By applying this battery, the minority charge particles are moving towards the junction. Those are nothing but majority charge particles are moving towards the junction, such as nothing but electrons. What we are expecting when the electrons are moving towards this p junction, p type region, there is a current. That current nothing but electron current. Okay, this current is nothing but then here 0.6 volts. 0.6 volts here, up to this level, the current is 0. Why? Because as I told you previous slide, here the silicon cut-in voltage is 0.6 volts. Up to this level, whatever we are applying external DC voltage is exceeding this level only. When that applied DC voltage is exceed this level, then only we are expecting there is a current. Okay, so then only the current is generated. That current is moving particular area here. Okay, so this is the current. Here it is initially voltage is 0, current is 0. By increasing the voltage, by slightly increasing the forward bias voltage, then the current is slowly increases up to this point. It is 0. Whenever we are applied voltage is exceeding this level, then only the current is going to increases. Means large number of major charge particles, they are moving towards this p side, and holes are moving toward this side. Then the current will be generated. This current is nothing but hole current. Sorry, electron current. This is the forward bias condition. Coming to the reverse bias condition. Okay, this is the reverse bias condition. This is p type and this is n type. For p type, major charge particles are holes. So it is denoted as positively charged area. For major charge particle n side is electron, such as negative. It is depend with a negative terminal. It is nothing but cathode, nothing but anode. Now we can apply the battery here as reversal here. Negative terminal is applied for positively charged area and positive terminal is applied for negatively charged area. Then what happens? Now let us observe here. The depletion region is increases. Why it is increasing? Okay, wide depletion region. It says here wide depletion region. How can the depletion region increases? Because of the electrons are moving this side, the holes are moving this side, means the charged particles are moving away from the junction. The charged particle in the n type, they are moving away from the junction. The charged particles are in p side, they are away from the junction. Then the depletion region is increases. Why? Because Here it is a positive charge. Here electrons are negative charge particles. So then the electrons are always looking towards the positive terminal or positively charged area. Here holes are positive charge ions. Here we are applying negative terminal. The holes are always looking towards the negative charge area. Then they are moving opposite direction. Then the depletion region is increases. Okay? Nothing but it is the reverse bias condition. Let us observe the what happened here. The electrons are moving in this direction, the holes are moving in this direction. Due to this voltage, reverse voltage, the depletion region is wider. And these are the immobile ions. These are the electrons, these are the holes near the junction, immobile ions. Okay? By increasing this voltage, at certain point, the device is act as in breakdown region. Breakdown region. What is meant by breakdown region? When we are exceeding certain amount of voltage, then the current is suddenly increased. So that voltage nothing but breakdown. Let us observe here the first point here. The reverse saturation current is not dependent on applied reverse voltage. If reverse voltage increased beyond particular value, the large current flow it damaging the diode. This is called as reverse breakdown diode. What it says? If reverse voltage is increased beyond particular value, large current flow it damages the diode. This is called reverse breakdown. Okay, it can take place due to the following effects: avalanche effect and Zenon effect. Here we can discuss about the avalanche effect. Okay, let us come into the diagram. By applying reverse voltage, that is the device going to reverse bias condition. So this is the way the charge particles are moving away from the junction. The junction is in increasing order. Okay, increasing order. So then the currents are in reverse direction. The electrons are in reverse direction away from the junction. The holes are away from the junction. Depletion region is increases. One more point here. Simply, anyone says the diode is in forward bias condition. Is there any current? Simply, you can say there is a current. The current is forward bias current due to majority charged particles. Another question. Again, another question rises. That is, suppose the diode is in reverse bias condition. Is there any currents? Simply, all the students are saying there is no current, sir. No current. But it is not. There is a current also. That current is nothing but drift current. Drift current. Nothing but it is reverse saturation current, I naught. Reverse saturation current, I naught. This current is available to the minority charge carriers. How it generates? This minority charge carrier current is generated. What I told you in previous, that is, in reverse bias condition, by increasing this level, at certain point, the current is suddenly increases. How it is increases? In this case, majority are moving away from the junction, but the minority are moving towards the junction. Why? Because this device is reverse bias condition for majority charge particles only, but forward bias for minority charge carriers in N side, minority charge carriers in P side. Okay. Then by increasing this reverse voltage, the minority charge carriers from N side they are moving toward this junction, and here the minor charge carriers are moving towards the junction. They are moving through this junction, and by increasing this voltage, they are moving in a way and hit to the other atoms. Then outermost atom will be releases the charge particle by increasing order. Then the large number of charge particles are increases by reverse bias condition. Due to that current, due to that large amount of charge particles, the current will be suddenly increases. Here, let us observe the graph. So this voltage, when the current is suddenly increases, that voltage what measure it is the voltage breakdown voltage for the particular device in reverse bias condition. Okay, so coming to the here, this is the reverse bias current, reverse saturation current. Let us see here, reverse saturation current. So this reverse saturation current is due to the minority charge carriers. This reverse saturation current is generated due to the minority charge carriers when the diode is in reverse bias condition. But actually, for minority charge carriers, the diode is in reverse bias condition. But actually, the diode is reverse bias condition for majority charge carriers. But due to the minority charge carriers, the diode is acting forward bias condition. So that minority charge carriers generating the current, that current nothing but reverse saturation current. Okay? Here, let us observe here. Initially, current is zero, voltage zero. By increasing the voltage, then the current is slowly maintain a constant level. If you are exceeding certain amount of voltage, then the current is suddenly increases. So this much of point here says breakdown voltage. Okay? Right. This is the basic overview of the reverse bias condition. Let us go to the next slide. Is VI characteristics. VI characteristics of PN junction diode. In previous slides, I discussed forward bias one region, reverse bias in another region. Now we can discuss about the VI characteristic, nothing but voltage and ampere characteristics. Voltage is on x-axis, current in y-axis. This is the forward bias region. Forward bias voltage. This is the breakdown voltage. This is the reverse saturation current. By increasing the voltage from 0 onwards up to this 0.6 volts, if this voltage, whatever we are applying, whatever we are applying the input voltage exceeding this level, then only the current will be increases. Up to this level, not consider the current. Okay, why? Because this is the cut-in voltage. Up to this level, the device does not changing conducting properties. If any changing properties are available, these are nothing but practically negligible. If your input voltage is exceeding this level, then only fully the device bring into on condition. On condition. Okay. Coming to the reverse bias condition. So here, in reverse bias condition, the diode will be act as a reverse bias, but here the current, there is no current generally, but there is a current. The current is generated due to minority charge carriers. So that minority charge carrier here is said as a reverse saturation current or leakage current. Leakage current. By increasing the reverse voltage at certain point, the current will be suddenly increases. So this voltage here nothing but breakdown voltage. VZ. Breakdown voltage. Okay, so this is the VA characteristics of the particular PN junction diode. Okay,